Now let's look at the problem of encoding arithmetic for all of the natural numbers. Since there are infinitely many natural numbers, we need infinitely many terms. One way to get infinitely many terms is to have a signature with infinitely many object constants. These constants are the only ground terms in our language. There's nothing wrong with this in principle. However, it makes the job of axiomatizing arithmetic effectively impossible, as we would have to write out infinitely many literals to capture our successor relation. An alternative approach is to represent numbers using a single object constant, let's say 0, and a single unary function constant, let's say s for successor. We can then represent every number n by applying the function constant s to 0 n times. In this encoding, for example, s of 0 represents 1, s of 0 represents 2, and so forth. With this encoding, we automatically get an infinite universe of terms, and we can axiomatize arithmetic with only finitely many sentences. What follows, we're going to use this second approach. Here's our signature. As we said, we have a single object constant 0 and a successor function s. We have one binary relation constant, same, which holds of two terms if and only if they're identical. And we have two ternary relation constants, one for plus and one for times. Unfortunately, axiomatizing Peano arithmetic is a bit more challenging than axiomatizing modular arithmetic. We cannot just write out the ground relational sentences to characterize our relations, because there are infinitely many cases to consider. For Peano arithmetic, we must rely on logical sentences and quantified sentences, not just because they're more economical, but because they're the only way we can characterize our relations in finite space. Let's look at the same relation first. The axioms here define the same relation in terms of 0 and the successor function. For all x, same of x, x. For all x, 0 is not the same as s of x, and s of x is not the same as 0. And for all x and for all y, if x is not the same as y, then s of x is not the same as s of y. It's easy to see that these axioms completely characterize the same relation. By the first axiom, the same relation holds of every term and itself. The other axioms tell us what's not true. The second axiom tells us that 0 is not the same as any composite term. It's also true of with the arguments reversed. And the third axiom builds on these results to show that non-identical composite terms of arbitrary complexity do not satisfy the same relation. Viewed the other way around, to see that two non-identical terms are not the same, we just strip away occurrence of s from each term until one of the two terms becomes 0 and the other one is not 0. And then by the second axiom, these are not the same, and so the original terms are not the same. Okay, now once we have the same relation, we can define the other relations in our arithmetic. The axioms here define the plus relation in terms of s, 0, and same. Adding 0 to any number results in that number. If adding a number x to a number y produces a number z, then adding the successor of x to y produces a successor of z. And finally, using same, we can write a functionality axiom for plus. The axiomatization of multiplication is analogous. Multiplying by 0 produces 0. If a number z is the product of x and y, and w is the sum of y and z, then w is the product of the successor of x and y. And once again, we have a functionality axiom. And that's all we need, just 3 axioms for same and 3 axioms for each of our arithmetic relations. Before we leave our discussion of Peano arithmetic, it's worthwhile to look at the concept of Diophantine equations. A polynomial equation is an algebraic expression composed using only addition, multiplication, and exponentiation with fixed exponents. That is numbers, not variables. For example, 3x squared plus 2y plus 2z cubed is a polynomial. A natural Diophantine equation is a polynomial equation in which the variables are restricted to the natural numbers. For example, the polynomial equation here is also a Diophantine equation and happens to have a solution in the natural numbers, namely x equals 2, y equals 2, and z equals 2. Diophantine equations can be readily expressed as sentences in Peano arithmetic. For example, we can represent the Diophantine equation 3x squared equals 1 with the sentence for all x, y, and z. If x times y, x is y, and 3 times y is z, then z is the same as 1. Okay, now I grant this is a little messy, but it's doable. And we can always clean things up by adding a little syntactic sugar to our language to make it look like traditional math notation. And for example, the expression shown here at the bottom. Once this mapping is done, we can use the tools of logic to work with these sentences. In some cases, we can find solutions, and in some cases, we can prove that solutions do not exist. This has practical value in some situations, and also has significant theoretical value in establishing important properties of Herbrand logic, a topic we'll discuss in a later segment.